we began last time to talk about uniform continuity. So let's just today focus on this topic. So remember what a continuous function does. A continuous function maps points that are nearby x to points nearby f of x. And what nearby is depends usually on x. So in general, delta will be a function of both x and epsilon. Correct? Now, something that is uniformly continuous, a function that is uniformly continuous, it's a stronger condition. It means that we can ensure that there is no need to specify x. Delta, the same delta works uniformly for all values of x. So let me show you a few examples in case this is new. So example 1, we can take, and that's important to specify the domain and range. So let's just take a function from R to R, which is given by f of x equal to x squared. I can draw the graph of this function. And using this graph, I can test if the function is uniformly continuous. What I can do is I'm going to select a sliding interval. So let's suppose that we have an interval of some short width. So this is at some point x. And here is the image of that interval. So what happens if we take this small interval and we move it out? What will happen is I can draw, for example, one interval somewhat farther here of the same width. So you can see that the width of the interval appears to grow. And as you push this interval farther and farther, you will see that this interval will move up and expand in size. So that means that this function is not uniformly continuous. You see that, right? Because that means that in order to make sure that the range interval is short, in order to make sure that all the points are within epsilon away from f of x, I will need to shrink the moving interval. So the way to phrase this is to say that the interval for any fixed delta x minus delta x plus delta is mapped to f of x minus delta x plus delta. So I just apply the function f to this interval. And what can I say about the diameter? The diameter of f x minus delta x plus delta will grow to infinity as x is pushed to infinity. So therefore, the function is not uniformly continuous. Yep.
If the interval starts to, instead of growing, if it starts to shrink, it can still be uniformly continuous.
No. Very important. Very important idea here is what? So, what is uniform? What is uniformly continuous? It means that that I can select a very thin stream. I think of it as actually just like maybe like a water gun, right? So water is pumped in this interval, and then you see where the spray is. So to say that the function is uniformly continuous means to say that the water is not the water can be the water spray remains focused as I move the interval anywhere, right? And that I can make the stream narrow enough, the input stream narrow enough, so the output stream is very focused. Do you understand my analogy, or? Kind of, right? Second. I'm going to give specific examples with delta epsilon. I'm going to show you that it depends on values, right? But you have to try to imagine what it means. Just try to imagine a picture of it. Yep.
Is this like basically the same as saying that the first derivative is bounded?
No, that's a condition that is actually very strong. It's actually Lipschitz condition. It's even stronger than uniform continuity, right? But that's one way in which you can make the function uniformly continuous. By the way, I hope you are reading Carothers. It's a good book, right? So this is like maybe a very, very loose commentary on a very big, fat book, right? So, yeah, but that's the problem. I mean, maybe I should have kind of constructed an animation, but really, what you have is when you think of uniform continuity, think about fixing your interval, your input interval, and then slide it everywhere. And if the output image of the interval is going to remain bounded, it's going to remain kind of short, then the function is uniformly continuous. And that has to happen for initial length. So in other words, you just, whenever you begin this experiment, you shrink your domain interval, and then you slide it from left to right, and you look if the image is going to grow. If the diameter of the image grows, or basically cannot be contained, cannot be shrunk to something arbitrarily small, then your function cannot be made. It's not uniformly continuous. I'm sorry. Yep.
So the diameter has to remain the same, or it just has? It's going to have an upper bound.
It has to have an upper bound. That's a good
lower bound.
Upper bound. Well, lower bound. I mean, well. For lower bound of the diameter, I mean, you know, if I fix it in one place and I shrink it, if the function is continuous, the image interval has to shrink. So that's what you understand with continuity. You keep this interval in one place, you shrink the domain interval, the image has to shrink. That's continuity. Uniform continuity means that I first shrink it and then I stopped. I keep it now of a particular size and then I slide it over the x-axis, left to right. And I'm just looking at the image. The image must remain somewhat bounded. And if I specify it initially to be arbitrarily small, to be less than epsilon, it will not grow beyond that. Okay? So, okay. Let's see. So using delta epsilon, so f is not uniformly continuous, as I mentioned. Let's actually show the dependency on A using standard delta epsilon argument. What can we do? We can basically show that if I take f of x minus f of a, that will be what? That will be x minus a squared, and then I will factor it. I will write it as x minus a times x plus a, and then I will make x plus a bounded by some k. So I'll make it less than or equal to k times x minus a. And when I make it bounded by k, if you remember the argument for delta epsilon for quadratic functions like this, how would I make this k? I will specify initial delta naught equal to say 1. And then that will imply that k is equal to, let's call this m of a, where m of a is max of 1 plus 2 times a, and absolute value of minus 1 plus 2 times a. So the way I obtain it is I make sure that x minus a is initially smaller than 1. If it's initially smaller than 1, then x minus a is between minus 1 and plus 1. And therefore, x plus a is between minus 1 plus 2a and 1 plus 2a. And therefore, this k, if I select the maximum of the absolute values, is going to be an upper bound. See? So, and then I can make this k times a.
It's supposed to be x squared minus a squared. Or just x?
Yes, you're right. It's supposed to be, thank you, x squared minus a squared. And that makes k times x minus a smaller than epsilon. So that means that delta of a and epsilon, here I write a epsilon, x is used as just a variable, delta of a epsilon will be the minimum of m of a, this k that I have here, it's m of a, and n1. So that's if you replace this 1 by another number, let's say by 1/2, you just have a different expression for m of a, you have a different delta. This is not a proof that the function is not uniformly continuous, but definitely this delta does not work. You can see this delta depends explicitly on both a and on, sorry, I made a mistake here. So it should be minimum of epsilon divided by m of a and 1. Yeah, now it's right. Okay, so this shows you that there is a dependency on a at least for this calculated delta. And by just looking at the picture, you see that there is no hope for finding a delta that does not depend on this a. Example 2. So here we have a function f from the interval 0 to 1 into R, and it's given by f of x equal to 1 over x. So then what you observe is that f of 1 over n minus f of 1 over n plus 1 will just simply be equal to 1, and this does not go to 0. That means that if I, well, I mean, you can actually see what's happening here in the picture for 1 over x. It's like this. So, and this is what's happening to 0. So if I take a small interval, what's going to happen to its size? It's going to be magnified as I approach close to 0. So if I'm sliding an interval, if I began with the interval of a particular width, here is the image of it, but then if I move really close to 0, the image is going to be huge. If I move the same size interval close to 0, notice I keep it the same size. So that would be something like this, much bigger. And the closer I move it to 0, the wider is this interval. So this fact tells you that the function cannot be uniformly continuous. All right. So you all see what happened here. It took a Cauchy sequence. This Cauchy sequence, it converges to 0, but it's not part of our domain. So it took a Cauchy sequence and mapped it to a non-Cauchy sequence. It mapped it to, basically it maps this Cauchy sequence 1 over n into this set of integers. So example 3. Well, the easiest example of uniformly continuous functions, in fact stronger than uniformly continuous, is, let's say, just a linear map, or, well, you call it a fine map, 3x plus 2, for example. So this function, let's take it to be from the reals to the reals. So if you just construct standard delta-epsilon argument, here is what would happen. So you would take f of x minus f of a, and that will create the function 3x minus a, which is less than epsilon if absolute value of x minus a is less than epsilon over 3. So you can just take delta of epsilon. Notice there is no dependence on this value a. Delta of epsilon is epsilon divided by 3. Now, in terms of what this function is doing, it's pretty clear why it's epsilon over 3. Geometrically, what is the function doing to the interval on R? On the domain, on the x-axis. Stretches it, exactly, by a factor of its radius is multiplied by 3. You see, so everywhere it's multiplied by the same amount. Everywhere the interval is expanded by the same amount. So if I slide it, no matter where, it's just going to be amplified everywhere exactly by the same amount. So that makes it uniformly continuous. Okay. So now let's consider more general examples. Example 4. So if I take a function f from MD to n rho, this function is called Lipschitz. If rho of f of x, f of y is less than or equal to some constant k times the distance from x to y. So this function is uniformly continuous. It's actually stronger than uniformly continuous, right? Is uniformly continuous. Because we can take rho of f of x, f of y, it's less than or equal to, I can say just simply delta of epsilon equal to epsilon divided by k. Okay. So in other words, this example was just a Lipschitz function where the constant was 3. So what this is saying is that if I think of m as the x-axis and I think of n as the y-axis, then the interval on the x-axis is not expanded more than a factor of k. Okay, and that makes it uniformly continuous. All right. So anyone here? So anybody still stuck? Doesn't know what's uniformly continuous, or you just don't want to tell me? Was the explanation sufficient for now, or no? You don't see it?
Yes.
Yes? Okay. I guess. All right, example 5. So let f of x be equal to root of x, and of course f is going to be from 0 to infinity into 0 to infinity. So then what you can observe is that absolute value of root of x minus root of y. There are a number of ways of noticing what I'm going to do here, but what is this? This is going to be the absolute value of root of absolute value of x minus 0 minus root of absolute value y minus 0. And the reason I do this is in this form it looks like a version of triangle inequality. Right? So this is just if you think of this as a metric space, this is root of absolute value of x minus y defines a metric. So that's one way to notice that. You can just kind of square it if you want to do a calculation and verify that this is so. But one other way to do that is to notice that the distance from xy equal to root of absolute value of x minus y defines a metric. On R. Okay? So then you can see that by triangle inequality, if you verify that it needs, in my notes I discussed, in the notes for analysis 1, I discussed ways of creating new metrics out of old ones, and that's where I discuss ways of producing it. So that's a quick way to notice that this has to be an inequality that holds. So in particular, this function is uniformly continuous. So f of x is uniformly continuous. And here is actually a test if you see it. So what should be delta of epsilon?
F squared of epsilon?
Well, I didn't say wrong, right? Yeah. So everybody write what you think and explain why. So remember what uniform continuity is supposed to be, right? So continuity, what's the picture? You draw the graph of the function, you fix a point x, you place a horizontal interval centered at x, and you shrink it. And what should you see? You look at the y-axis, and what should you see? If it's continuous, what should you see on the y-axis? A shrinking interval on the y-axis. How do I know it's going to be an interval on the y-axis? Well, because the image of an interval is an interval. Remember, by connectedness. Okay? So that's how I know that if I see a picture for continuity, just for R, for a function from real numbers to real numbers. Horizontal interval shrinks means vertical interval shrinks. The vertical interval is not going to move, it's just going to shrink. Okay? That's the picture that you think about when you think of continuity at one point. The rate of shrinking will be different if you select a different point. Now for uniform continuity, what should happen is you select a point x, and for that point, you are going to shrink your interval. But not to 0. Just shrink it to some point. Now it's x minus delta, x plus delta. And then what you're going to do, you're going to take this interval and you're going to slide it from left to right. As far as possible left, as far as possible right, move it around. And what you look at? You look at the y-axis. On the y-axis, there will be some sort of traveling shape. That shape will always be an interval. Do you see why it's always going to be an interval? Because the image of an interval under a continuous function has to be an interval. Assuming the function is continuous, of course. Right? If it's not continuous, there is no need to speak of uniform continuity. So what should I see? I should see that I can make it smaller than, I can make the range interval smaller in radius than epsilon. And no matter how I move this domain interval, the range interval is going to stay smaller than epsilon. That's uniform continuity. If it fails, the function is not uniformly continuous. Okay? So this delta of epsilon here, you see why it would not fail. Root of x minus root of y is less than or equal to root of absolute value of x minus y. So that means that I can take, as you said, epsilon squared. Why epsilon squared? If x minus y is made smaller than epsilon, this thing is smaller than, so if x minus y, absolute value, is smaller than epsilon squared, root of x minus root of y is smaller than epsilon. Correct? So Lipschitz. Sorry, not Lipschitz. By no means, I'm sorry. Not Lipschitz. Only uniformly continuous. That's the example that it's not Lipschitz. How do we know it's not Lipschitz? That's, by the way, in terms of what you mentioned, right? So so the derivative is not bounded. But f of x equal to root of x is not Lipschitz, so why is it not Lipschitz? Because if it were, so you can just take absolute value of root of x, which is just absolute value of root of x minus root of 0. If it were less than, if it were Lipschitz, that would be less than some k times x minus 0, which is just basically some k times x. That is, if it were Lipschitz. Then this will follow. But then what you can do is then you can just take root of x divided by x will be then less than k. But this is just 1 over root of x. It's supposed to be then less than k. But this guy grows to infinity. As x goes to 0 plus, this guy will grow to infinity. That means that it's impossible to make it Lipschitz. You see what I did? I tried to make it Lipschitz. So I tried to make the distance of the function from root of x to 0, let's say, less than absolute value of k minus 0, which is the Lipschitz condition. But that implies that if I divide it around, that root of x over x is a bounded function for all x. That cannot be the case. Because near 0, this is unbounded. Another way of saying that is the derivative is unbounded near 0.
So if we said, for example, f takes left closed 1/2 comma infinity.
Yes, that would be Lipschitz, absolutely. Right? The obvious example is if the derivative is bounded. Think about it. You can use the mean value theorem. If the derivative is bounded, the function will be Lipschitz. Will not only be uniformly continuous, but will be Lipschitz. Okay, so quick comprehension check. So first is continuous functions. Send Cauchy sequences to Cauchy sequences. So make sure that if you say true or false, you give an example. 2. Well, let me not write 2 just yet. Let's just keep it for a moment at 1. So, is it true or false?
You just read that one.
Continuous functions send Cauchy sequences to Cauchy sequences. True or false?
Didn't we just do an example where?
Maybe we did, right? It's all good. So it's too simple.
No, I'm asking. I think no. By the 1 over n.
We just did an example. That's true. You're staring at it. All right. So the answer is obviously false. Example 2. Okay. Okay, 2. So uniformly continuous functions. Send Cauchy sequences to Cauchy sequences. Is that true now? So this is true. So example is of course not. You need to prove it. So actually, in the theorem that we provide now, we're going to talk about now, this is enough to explain why this is true. All right, proposition. If f from m to n is uniformly continuous, then f maps totally bounded set to totally bounded sets. To proof. So the proof is not terribly difficult. So we assume that the function is uniformly continuous, and we take a totally bounded. Then what we want to show is that f of a is totally bounded. Now, how do I establish that it's totally bounded? The easiest way is to tear this set into pieces and show that there are only finitely many small pieces. So I can do that by tearing the set A into small pieces. So if A is totally bounded, I can say that A is equal to the union of I1 to n of A sub I, where diameter in M of A sub I is less than delta of epsilon, where the delta of epsilon comes from the fact that the function is uniformly continuous. So I'm going to tear it to small enough pieces so that the image of each piece, you see any point in here, any x and any y in A sub I, its distance, their distance is going to be less than delta. That will imply that the distance of the image of f of x and f of y is going to be less than epsilon. Right. So the implication is that f of a is just equal to the union from I equal 1 to n f of ai, and the diameter in f of ai is smaller than epsilon. So we're done. Proof complete. So this in fact will imply that Cauchy sequences are mapped to Cauchy sequences, right? Because Cauchy sequences are just their image is totally bounded. Okay. All right, so a very important theorem is basically that on compact sets, all continuous functions are very well behaved. let M be compact. And f from M to N continues. Then f is uniformly continuous. Proof? Well, one simple way of doing that is that we assume that the function is continuous, so we're going to then select balls of radius delta, and the delta depends on the x where I pick it. And I'm going to create an open cover. So what I'm going to do is, for each x belonging to M, let delta sub x be such that the image of f, the image under f of the ball of radius twice delta x centered at x is going to be contained in a ball of epsilon over 2 centered at f of x. So again, the reason I picked such constants, you can just, if you play this, if you look at this proof, if you play this game, you just adjust your constants so it works. So here is what happens then. So you agree that I can do that. For any x, I pick an interval, I shrink it around that x, the image should shrink. So I can definitely do this for any x, but the rate at which shrinking happens will be different for different x in general. So what we now have is that we now have an open cover. So the balls of radius delta x centered at x, where x is an element of M, is an open cover of M, which therefore has finite subcover. And the finite subcover, let's list it. Maybe this is going to be some ball of radius delta x1 centered at x1 all the way to ball sub delta xn centered at xn. That's going to be the finite subcover. Let delta be the minimum. If the distance between x and y is less than delta, observe that x has to be an element of, let's say, ball of radius delta x sub k. For some k, correct? This is an open cover, so every element belongs there. So my goal, first I know that x is somewhere, and then my goal is to see where is y. Y could potentially be in a different ball, correct? So that's the thing. So if x is there, then what we now have is that the distance from y to x, I want to know how far is y away from this, how far is y away from xk. This is less than or equal to the distance y to x plus the distance of x to 2xk. Now the distance from y to x is less than delta, and the other distance is less than delta x sub k. Now I pick delta to be the minimum. So that's less than or equal to delta x sub k plus delta x sub k, which is 2 times delta x sub k. So that implies that x and y, they both belong to the ball of radius twice delta x sub k, centered at x sub k. Which implies that f of x and f of y are elements of the ball of radius epsilon over 2, centered at f of x sub k. So that means that rho f of x to f of y is less than or equal to rho f of x, the distance from f of x to f of x sub k, plus the distance from f of x sub k to f of y, and each of them is less than epsilon over 2, and we're done. There are other proofs, of course, but this one is, I think, the simplest. Any questions? The compactness, notice I picked the open cover and I was able to reduce it to a finite subcover. And that ensures that I have a minimum delta. You see, so in a sense, basically, any x is going to be within some delta xk away from one of those points. And then if I shrink y close to x, I will force uniform continuity. If I don't have this finite subcover, then taking the minimum delta might be impossible. Minimum delta might be 0. Okay, that's what this does. So it's at this step where I need compactness. So that gives you a very strong condition. It tells you that however complicated is your function, if your domain is compact, the function is uniformly continuous. So an easy example is just take, again, x squared. You can actually compute it directly, but if you take f of x equal to x squared, you see that if I now specify the domain to be a closed interval, the function is going to be uniformly continuous. Now if I restrict, let's say, the interval from 0 to 1, 0 to 1, and the function is f of x equal to x squared, then what we have is f is uniformly continuous. Okay? Okay, so this ends the topic of uniform continuity. Before I move on, do you need more examples? Do you understand that for example, if the derivative of the function is bounded, like you suggested, then the function is Lipschitz? Do you see that? No need to go over it?
Yeah, you go over it.
Okay. So example, if we have f from R to R, or from some interval, it doesn't have to be from R, right? From R to R, where f prime of x in absolute value is less than some k, f is Lipschitz. Why is it Lipschitz? Well, very simply, just take absolute value f of x minus f of y. Then this is the same as absolute value f of x minus f of y divided by x minus y, times x minus y. Now we assumed by the mean value theorem, this is going to be some f prime of c. And that's by mean value theorem. And of course, this implies this is less than k. For whatever f prime of c is, it's less than k times x minus y. So that's a very easy way of checking if a function is uniformly continuous if you know it's differentiable. So it gives you a lot of examples right away of even stronger than uniform continuity. So, okay. So I'm going to skip a lot in chapter 8, but at least I'm going to show you that that all the norms are pretty much are strongly equivalent if you're dealing with a finite dimensional space. Normed finite dimensional vector spaces. So definition. Two norms, which I'm going to write, one of them I'm going to write like N1. And another one and 2 are strongly equivalent if there exists some k, if for some little k less than k, we have that little k times n2 of v is less than or equal to n1 of v less than or equal to big K n2 of v. For all v. So strong equivalence actually will imply that under norm n1 and under norm n2 we have the same Cauchy sequences. We have the same conversion sequences, obviously. We basically have the same sets that are bounded, the same sets that are totally bounded. Pretty much strong equivalence is a very, very, very strong condition. It tells you that you have the same open and closed sets, exactly. So it tells you that the structure of the space under n1 or under n2 is exactly the same structure. You have the same derivatives, for example, right? You can calculate you can calculate derivatives with this norm. So basically, given a norm, you can calculate what's the derivative at some vector v. It doesn't have to be an element of Rn. Okay, that's so. So why is this interesting? So the way you define the derivative is something like this: limit as v goes to u under, let's say, the n1 norm of f of v minus f of u minus some linear map t of v minus u divided by, let's say, maybe the n1 norm of v minus u. That will be the definition of derivative.
Should the numerator have
Should be equal to 0. No, the numerator doesn't have to be taken in the norm. There is no need for it. Right? The denominator has to be. So you can define, let's say, so if you do analysis on manifolds, you can do that under the Euclidean distance roots, or you can do that under the sup norm, right? Just that would create squares. Let's say when you look into some of you are taking calculus on manifolds, so the open sets there, the open balls are squares. Right, so this formula will then be independent of what you select N2 to be. Is it over open balls or over squares or over anything? And in fact, this will tell you that you can create this. You can define derivatives even for vector spaces on which derivatives initially did not make sense. So you see, a finite dimensional vector space might be the space of all linear maps from Rn to Rm. So it could be just something that seems a little bit weird when you talk about differentiation there. All right, so here is the theorem that I want to prove. Theorem: if this is independent of norm. You are free to just basically switch from norms. You can prove results. If it's easier to prove it for a square, you use a square. If it's easy to prove for a disk, you use a disk. So the theorem is if V is finite dimensional, vector space, any two norms, and 1 and 2 are strongly equivalent. Proof. So first we're going to fix a basis. Basis v1, vn, define so I'm going to make n1 a very concrete norm and n2 to be any norm. So I'm going to show that every norm is strongly equivalent to a very concrete norm. So the way I'm going to define n1 of v, it's going to be, given this basis, it's going to be n1 of a1 v1 plus an vn. And that's just going to be, I'm going to define it to be the absolute value of a1 plus the absolute value all the way to the absolute value of an. So I'm defining it to be just translate the coordinates and take the one norm of the vector a1 through an. Okay, so it's basically just translating v1 into v1 through vn into the coordinate vectors e1 through en, and just takes the norm. If n2 is any other norm, yeah, by the way, I see that some of you are tired, and I actually truly understand you. When I try to go to sleep, those things just roll in my mind without stop. It just makes me want to vomit. Like, honestly, I'm always talking about calculus and manifolds and whatnot, but really, Sometimes I just basically it's like I'm trying to survive and I'm falling into a spiral and I'm trying to survive, and I think if I stop calculating for a moment where I am or my coordinates, I'm gonna lose myself. It's just so complex and so disgustingly horrible that you're spinning in it and you're just losing your orientation. Okay, so just hopefully that gives you a little bit strength to. Right. No, on infinity, right? That's just, let's say, if you think about fractals and whatnot, it seems like such an interesting topic, and you can just talk about it in such wonderful ways about the complexity of the geometry. But I feel right now I feel like it's as if you eat something and you vomit it out, and then you eat it again and you vomit it out, and you eat it again and vomit it out, and that's the recursion, right? That's what generates this complicated geometry that I have to study and present it before in the extreme length seminar. So, all right. So. Sorry if because of that I'm not sounding as exciting as this material deserves. Right? I am excited somewhere deep in my mind, somewhere back, right? But then I'm talking to you like norm vector spaces, epsilon delta, and 1 and 2, right? So I understand. Sorry about it. Hold on a little bit. We're almost done. If N2 is any norm, then what we can do is remember what norms do. What do norms do? What do norms do? What do they do? Easy language. What is a norm? What is it doing? Measures the length of a vector, exactly. Nothing else, right? So in particular, it has the triangle inequality, and it has the scalar factorization property that you can just factor under absolute value. So what we have is that if N2 is any norm, N2 of V is the same as N2 of A1 V1 plus and that is less than or equal to absolute value A1 N2 of V1 plus absolute value an and 2 of vn. So what I did here is I just used triangle inequality on norms, and I factored out basically the norm of this segment is just absolute value of a1 times v1, right? And I use triangle inequality here. So now if you look at this expression, this looks very similar to this expression. So all you do is just say that this is less than or equal to the maximum of N2 Vi, where I ranges from 1 to n, times what? Times
The L1 norm.
yeah, the exactly. So this thing times the L1 norm. So let's call this K times, so this is the big K times the N1 norm. Okay, so one direction is very easy. Now the other direction requires compactness.
Can you also show that it's greater than or equal to little k N2?
Yeah, I need to show the little k, exactly, right? The little k is where I'm going to use minimum, right? Where I'm going to use compactness. That is, I'm going to show, so what this means, in fact, so notice that this makes N2 a Lipschitz function.
Why do you need compactness to show the minimum? I mean, it's a finite list, so it's just the minimum.
Well, it's not a finite. It's finite only v1 up to vn is finite, but not all the possible directions. Right? Those could be infinite. So we don't need the minimum. Right? So what we now have is, moreover, I can think of N2 as a function from the vector space V with norm N1 into R. So this function is Lipschitz. And why is it Lipschitz? Well, just take absolute value N2 of V minus N2 of W, this is, by the fact that N2 is a norm itself, this is going to be less than or equal. It's one of the triangle inequalities, right? That you hopefully recognize. This is less than N2 of V minus W, which according to what we just showed, it's now N2 of any vector is less than some capital K times. Exactly. Do you see it? So in particular, N2 is continuous. So N2 is continuous. So here is where I use compactness. So for V belonging to,
Shouldn't that be less than or equal to K N1 V minus W?
yes, it should be. Thank you. So for V belonging to capital V and not 0, what I can do is I can take, and by the way, writing N1, maybe I'll write it as just also K times V of one norm. So that would be the one norm of V, since it's pretty much the same, right? So then what I can do is I can make this a unit vector. So that would mean that V divided by the magnitude of V, it's going to be an element of the circle of radius 1 centered at 0, which is simply the set of all W such that the one norm of W is equal to 1. And this is compact. Compact. Very important point. Compact in the space. Would it be compact if I make it an infinite dimensional space? We saw examples of that.
Yeah, it's not, because you can have the sequences where you just have 1 and then 0.
Right. Remember that just take the unit vectors, take the coordinate vectors, and we saw that the coordinate vectors, their distance in the one norm is going to be what? 2. And this would be homeomorphic to the, what is it called? To the discrete space. So if it's infinite dimensional, it's not compact. Do you see the? So one thing that I'm not going to say more about, just to verify that this is compact. Verify. So then, so hence, N2 attains max and min on C1 of 0. It has a maximum. So basically, on the circle, there is a maximum and minimum. So this map N2, it can be thought of as what it does. It basically takes the circle and maps it to some interval. And somewhere is going to be a minimum. Okay? That's the picture of it. So what you then have is then that means that N2 of V divided by basically the normalized V, it's going to be bigger than or equal to this minimum, which is little k. That's the minimum. And that implies that, you see, this is a norm. So what it implies is that I can factor out this normalization. So I can factor out and make it 1 over the n1 norm times n2 of v. That's bigger than or equal to little k. So that means that n2 of v is bigger than or equal to little k times the size of v. And the proof is now complete. Okay. So the next topic that we're going to do is, if you can read it ahead of time. It's going to be chapter 9. I'm skipping a few things from chapter 8. And we're going to discuss discontinuous functions and category theory. Okay, that's going to be, hopefully we'll cover that quickly. And hopefully it's going to be interesting. We're going to talk about unions of closed sets and intersections of open dense sets and stuff like that. Okay, and popcorn, if you like popcorn. Right, there is a popcorn function. Right, all right, guys, have a good one. Thank you.